All right, so the third law of thermodynamics is essentially just saying as we approach absolute zero, the entropy of that sample is going to approach a constant. And if it's a pure substance, it's going to be zero entropy. And if it's a impure substance, it could be zero entropy overall, or it might have a small amount, just depending on the way those different atoms or different molecules kind of freeze in place. But then as we go from absolute zero to just any other temperature, so as we start to heat up that sample, now those molecules are going to start to move, and we're going to see the entropy is going to increase as we increase the temperature. So if we look at the table here, these are just standard entropies. And essentially what that means is just the entropy of these different substances at standard conditions. So we're thinking about 25 degrees Celsius or 298 Kelvin, and then just 1 atmosphere. And with it, you'll notice as these molecules get larger, the entropy is typically going to increase. And that's going to be just because these molecules are going to get more complex. We're going to have more of the microstates. And we're going to see the entropy is just going to increase if we look at this is the alkane series, so just hydrocarbons with an increasing number of carbon. We're going to see the entropy here is going to increase because now we're just going to have more opportunity for the rotational movement, the vibrational movement. We're just going to have more of those microstates. That's why we see of these 3 hydrocarbons, propane is going to have the highest entropy, just because it's going to be the largest molecule. And then when we're looking at calculating the entropy change, we can do a calculation similar to when we're calculating delta H. If we look at the enthalpy, in that case, we could look at the enthalpy for the products and just sort of add all those up and then subtract from the entropy or enthalpy for the reactants. We're going to be able to do the same thing with the entropy here. And then with that first sentence at the top, that box just got formatted weird. That should just be the delta sign, so change in enthalpy there. But like I said, this equation is going to be essentially the exact same. It's just now we're looking at entropy, so we've got delta S rather than delta H. But remember, delta anything is always going to be final minus initial, so we still have products minus reactants here. And then with it, N is just going to represent moles. So that's going to be the moles of that specific substance. So on the product side, if we've got multiple substances and we've got a coefficient of 2 in front of one of those substances and a 3 in front of the other, we would multiply each of those entropy or change in entropies by that number of moles just to account for sort of the scale of that reaction. So if we look at a question like this, calculate delta S for the synthesis of aluminum from aluminum oxide and hydrogen. So with it, we would need to know the entropy of these different substances, but then we can just plug it into the delta S equation. So looking at it, to start, we've got 2 times 28.32. And with it, normally you'd have to have a table, so you don't have to, of course, memorize these entropy values, but this would come from some sort of table. But that's going to be describing the aluminum, and then we're adding that with the 3 times 188.7 because that's going to be referring to the water. So that's our products. So we're going to add both of those up, and then we'll essentially just do the same thing with the reactants on the other side. But now we're going to take the difference between those two. And if we look at the final answer here, we'll wind up with about 180 joules per Kelvin. And it makes sense why this reaction in particular would be a positive delta S. So this reaction is becoming more disordered. It's becoming more random. Because if we look at the substances here, and the way it's set up, we can kind of compare them pretty easily. We've got a solid on both sides and a gas on both sides. So if we just compare each of those states of matter with the same state, we can look at the aluminum oxide and the aluminum. And with it, the aluminum, since it's just aluminum by itself, is going to be more ordered. So we're going to have lower entropy there. So it's 28.32 times 51. But with it, now we have 2 moles of aluminum compared to just the one for the aluminum oxide. So we're going to see the entropy overall from the solid pieces is just going to increase slightly. It's going to be 56.64 on the product side compared to 51 on the reactants. And then if we do the same thing with the gas, in each case we've got 3 moles, but it makes sense why the entropy of water is going to be higher, because now it's going to be a larger molecule. So if you think about the hydrogen atom, or hydrogen molecule, excuse me, it's just going to be those 2 atoms. We're just going to have that one bond. But now with the water molecule, we've got an additional bond there. So it's just going to be a larger molecule. We'll see increased entropy. That's why we see 188.7 for water compared to 130.58 for the hydrogen. And if we look at the Haber process, so taking nitrogen and hydrogen, combining them into ammonia, we're going to see the entropy change for that system is going to be almost negative 200. So it's going to be becoming more ordered. And that's going to be representing the system. So if we're thinking about the entropy change for the universe, we've got to also consider the surroundings. And when we do that, we can use the equation negative Q system, because if we think about the direction of that heat, if it's going into the system, that means it would really just be leaving the surroundings or vice versa. So that value is going to be the same. It's just going to be kind of the opposite sign, because we're looking at it from the reverse perspective, divided by the temperature change. And again, this is going to be for an isothermal process, so assuming that the temperature is going to be constant throughout. And if we also had the pressure constant, then the top piece of this equation would essentially just become the enthalpy. So we can just have delta H there. And with a spontaneous process, remember the entropy of the universe is going to increase. So it's going to be greater than 0. We're going to have a positive value there. And what we can do is take these equations. And if you think about, again, the change in the universe overall is going to be the change in the system plus the change in the surroundings. And we can take the delta S surroundings, and like we saw in the previous one, kind of substitute it in based on the heat and the temperature there, so we can change the term. And then we can multiply everything by negative delta T just to get rid of that fraction. So on the bottom line there, the right-hand side of that equation is just flipped. So now delta H is just coming first, but we're just multiplying everything by negative delta T there. And what we're ultimately going to have this equation be is Gibbs free energy. So the left-hand side of this reaction, negative T times delta S, is just going to be representing delta G ultimately when we typically write this equation. And like I said, this is going to represent Gibbs free energy, and this is going to be how we can determine if a reaction is going to be spontaneous or not. And in this equation, so we're going to, for a spontaneous process, the delta S for the universe is going to increase, so it's going to be positive. So if we have a positive delta S in this equation, the left-hand side of it, this Gibbs free energy delta G, is going to wind up being negative, just because the positive delta S times that negative temperature is just going to give us a negative number. So we're going to see a reaction is going to be spontaneous, or a process is going to be spontaneous when negative delta, or when delta G is negative. So with it, if delta G is negative, that's going to mean the forward reaction is spontaneous. If delta G is 0, that just means the system's going to be at equilibrium. And then if delta G is positive, the reverse reaction is going to be spontaneous. So kind of similar to delta H. If it's exothermic in one direction, it's going to be endothermic in the other, similar to the Gibbs free energy here. Okay, but now if we look at the question here, calculate the standard free energy change for the formation of NO from N2 and O2. So this is going to be the delta G that we're looking for. And then we've got the equation nitrogen plus oxygen gives us 2 moles of nitrogen monoxide. Given that delta H is 180.7 kilojoules, delta S is negative 25 almost. So again, delta G, delta H, minus T delta S. So with this one, we've got the delta H, and what I'm going to do is just make sure that these units match up, because if you look, kilojoules and then joules, I'm just going to make this joules right away, so I'm just going to move that decimal over 3. So we'll have 180,700 joules minus the temperature. We've already got it in Kelvin, so we don't have to change that at all, minus negative 298 Kelvin. And then with the delta S, again, we've already fixed the unit, so we can just plug in. We should have a decimal there. What is that? And then with sig figs, we want 3. So then we'll round this to 188 kilojoules. So with this one, we'll see that this reaction is going to be spontaneous, or it won't be spontaneous, excuse me, because we've got a positive delta G. So with the Gibbs free energy, negative delta G is going to be spontaneous. So in this case, since we've got such a large positive enthalpy change, we're just not going to see this reaction occur spontaneously. And also, the entropy change is negative, so sort of both of those terms are working against the spontaneity of this reaction. And then just like we saw with the entropy equation, we can kind of have the exact same thing just with Gibbs free energy as well. So since they're all going to be state functions, we can just look at the products, total all those up, and then subtract the reactants from it. That change is going to be the same as the free energy change for the reaction as a whole. And then again, N is just going to represent the coefficient in the balanced chemical reaction for each of these substances. Oops. All right. So looking at this question, we've got 2 different pieces. First, we want to calculate the standard free energy change for the reaction. So if we take P4 and react it with 6 moles of chlorine gas and get 4 moles of phosphorus trichloride, what is the delta G of that reaction going to be? And then with the second one, we want to think about what's the delta G of the reverse reaction. But looking at A first, again, we're just going to do products minus reactants. So delta G will equal 4. And I'm going to leave out the units here, but since we've got 4 moles times, 269, not 296. But since we've got 4 moles times negative 269.6 kilojoules per mole, the moles is going to cancel. We'll just be left with kilojoules. And that's all we have on the product side. So that's we can just kind of put that in parentheses. And then on the reactant side, chlorine, Cl2, just going to have a free energy change of 0. So we can kind of just ignore that piece, just focus on the P4, and we've only got 1 mole of that. So we don't even need to really multiply this by anything. We'll just have negative 24.4 kilojoules. And we're going to see the delta G here will be 4 times negative 269.6 minus 4, just under 11, negative 11. That would be kilojoules. So what we're going to see is this would be a spontaneous process then, since we've got a pretty large negative delta G there. All right. But with the G with the degree sign is just representing the standard. It's going to be 25 degrees C. How can we calculate this at other temperatures? Oops, these look like they got a little. Yeah, these look like they got a little mixed. But we can use this equation just to calculate delta G at different conditions. So R is just going to be a constant. T is going to be the temperature in Kelvin. And then Q just representing the concentrations of those substances. So when we have concentrations of 1, when we have standard conditions, Q is just going to be equal to 1. So that whole term just winds up being 0. Let me go back for a second. But when we look at delta G, when we look at that equation, delta G is equal to delta H minus T delta S. We've kind of got two of those terms there. We've got delta H, and then we've got the entropy change as well, delta S. And of course, both of them are then going to affect if a reaction is spontaneous. But depending on the sign of those values, and then depending on the temperature at which that reaction is occurring, we can kind of use that information as a whole to determine if this reaction is going to be spontaneous or not. So if we look at this next table, this will go. If we look at this next table here, again, we want to think about delta G being negative. So that means we would prefer delta H to be negative. And then since we have negative T delta S, a positive entropy change would make it more likely to be spontaneous as well. So we want a negative delta H, a positive delta S in order for spontaneity to be guaranteed. Because in that case, no matter what the actual values of each of them are, no matter what the temperature itself is, both of those terms are going to wind up being negative. So delta G in that case has to be negative. If we flip them around, if we've got a positive delta H, we've got a negative delta S. Now both of those are going to be working against spontaneity. So no matter what the temperature is, that reaction won't be spontaneous. But when we've got the same sign for both of those, then the temperature is going to determine when that reaction will be spontaneous. So with the first one in this, or the third one technically, I guess. But if we've got a negative for both of those terms, so negative delta H and negative delta S, that means the enthalpy, that delta H, is working towards spontaneity, so it's going to make it more likely to be spontaneous. But the negative delta S, since we're multiplying it by the negative temperature, that term is then going to become positive. So we want, again, delta G to be negative in order for spontaneous reactions to occur. So in this case, if the reaction wants to be spontaneous and we've got both of those signs being negative, we need the enthalpy piece to be dominant, essentially. So what we want then for the entropy is for it to be multiplied by a low temperature value. So at lower temperatures, we're going to see reactions that have negatives for delta H and delta S. We're going to see at low temperatures that reaction is going to be spontaneous. But as the temperature increases, that reaction will switch to not spontaneous. And then if we've got a positive sign for both of those terms, it's just going to be the opposite. In that case, we want the T delta S to sort of take precedent. So we want that temperature to be high, so that value is larger. And then we want the enthalpy change. We want that positive delta H to be a small number. And again, that's thinking in terms of wanting a spontaneous reaction. And then you can see some examples here. So if we look at the third one there, the first one that includes water, we can see spontaneous at low temperatures, non-spontaneous at high temperatures. So liquid to solid, so it makes sense at low temperatures, that reaction is going to be spontaneous. We're going to have that substance freeze, but at higher temperatures, we're not going to have that process occur. And then just the reverse with the next one, now we're switching it around, going from solid to liquid, so we're looking at melting. So we're going to see at high temperatures, we'll melt that substance, but at low temperatures, that's not going to happen. Oops, and this one, again, we would need the the actual negative or change delta G for the standard conditions in order for this reaction. I didn't put it in the slide. But if you think about it, we would have that, we would have this value. We would need to have that value. Again, we can't just memorize those for every substance. So that would have to be provided in the question. I just forgot to put it there. R is just going to be a constant. The temperature we have in this case, so it's actually going to be 298 still. But for this one, we don't have the concentrations being standard, which means just concentrations of 1. So in this case, what we would be doing is focusing on that Q. And then we would have the partial pressures. We could essentially just square for the ammonia on top, products over reactants, take the nitrogen, which is 1, and then, and with this reaction, it's not balanced there. There should be a 3 in front of hydrogen, so we want to make sure we cubed the hydrogen pressure there. And then we can see just one other sort of rearrangement in terms of this Gibbs free energy equation. So if we're thinking about equilibrium, Q is going to be equal to K. So those concentrations are going to, when we multiply and divide, depending on the specific equilibrium expression itself, we're going to see that value is going to be equal to K. So at equilibrium, remember, that free energy change is going to be 0. So when we look at the equation, the left-hand side, now delta G is just equal to 0. So we can rearrange it even further. Subtract RT ln K from both sides. And then divide, if we wanted to divide by negative RT again, get ln K by itself, raise it to the, have the E in there to just isolate it. And then with K, it's going to be equal to that term we see at the very bottom. So if we look at the question here, using the standard free energies of formation to, I didn't put it on this one either. So let me pause it so I can see what those are. And they're already included at the bottom. But with this equation, we'll have K is equal to E, and then we'll have negative delta G RT. Whoops. Whoops. That's not what I want to do. So again, we're just using the bottom version here because we're solving for the equilibrium constant in this case rather than the delta G value. But once we have that equation, now we're just going to plug in those different pieces of information. And the exact value for R. So K is equal to E. So that'll really be positive. Since we're going to do negative delta G and delta G itself is negative, we'll really have 8,000. And then with it, we'll have joules per mole. Oops. And then R is going to be 8.314 joules per mole. Oops, I got that fraction there, joules per mole Kelvin. And then with the temperature in this case, we've got 225 degrees C. So that'll be 298.15 Kelvin. And what we're going to see there is the units in that exponent are all going to cancel. So when we divide joules per mole by joules per mole Kelvin, of course, joule and mole both get canceled out. But now we've got Kelvin there. But that's going to be then canceled by the Kelvin in the temperature value. So with this one, we will have E to 33,300 divided by 8.314 divided by 298. Just write it on this side. But what we're going to see in that case is the equilibrium constant is going to be, how many sig figs do we want? 3 sig figs. So we'll have 6.83 times 10 to the 5th.